So here we are going to talk about forces and go into the first law of motion, or Newton's first law. So first off, let's remind ourselves about vectors. So if you're not so sure on vectors and scalars, you don't know what I'm talking about with that, make sure you go and check them out before watching this video. So forces are vectors, which means they have a magnitude and a direction. And that's why we use arrows to draw forces. So the size of the arrow represents its magnitude, and obviously where the arrow is pointing represents its direction. So the larger the length of the arrow, the larger the magnitude. In certain examples, you may need to draw vectors to scale, and so they may give you graph paper in certain questions, or you may need to use a ruler. So be aware of that. I'm not going into them in this video though. So what are the main examples of forces that we need to know? So the main one, the main ones that we need to know. The one that everyone remembers is, of course, weight or gravitational force. Don't call it gravity, as sometimes that's not accepted. So weight and gravitational force, anything that has a mass and is within a gravitational field, so is within something like a large planet, which has a gravitational field, is going to have a weight or gravitational force on it. The next one is the one that confuses a lot of people. So reaction or normal force. So if someone is standing on the ground, the most common mistake is when they're labeling the upwards force coming off the ground, they call it up thrust. It is not up thrust. We'll talk about up thrust in a second, but this is the normal or reaction force. Okay, so you've got your weight pushing you downwards, and the weight your weight causes you to push you left, or your feet push into the ground, and the ground pushes back with a reaction force, okay, which stops you going into the ground. It's just the same as if you were to lean into a wall. Okay, so if you were leaning into the wall, you would feel, or if you lean into the table, you would feel the normal or the reaction force back off the wall. So anything that's on the ground and is in contact with it, or in contact with something, would be called the reaction or normal force. Electrostatic force would be things like, if you think of anything that's statically charged, so if a balloon is sticking to the wall, that would be an electrostatic force. Magnetic is obviously magnets. Thrust, now this one does confuse people a little bit. So for thrust, if we think of a rocket, okay, so a rocket is jetting out propellant, okay, and that gives it, and it's jetting out the propellant backwards, which causes the rocket to feel a force forwards, okay, and that's due to Newton's third law, which we'll go through in a different video. But so thrust is anything that is putting something out backwards to move forwards. So if you think of I don't know, like a boat with a propeller, or a jet ski that pushes water out backwards, and then therefore you would feel a force forwards. Okay, so that is thrust. What do we mean by up thrust then? So up thrust is, if you think about when you push a ball into water. Okay, so you've got a ball and you're going to push it into water. You know that the more that you push downwards, that you feel that the ball wants to push back upwards. Okay, because the more of the water that is displaced, more of the object that is under the water, the bigger the up thrust force it feels. Okay, so we notice up thrust more when anything is in a fluid. It would feel this upwards force when it's in a fluid. Now, technically, there is up thrust on us all the time. Just from the air that we displace around us, there would be this tiny force upwards on us. Okay, now we don't ever label that on anything because it's so negligible compared to our weight. When is it noticeable? Well, if you think of a helium balloon, well, that displaces the fluid, the air around it, which causes an upwards force, and it's noticeable because the weight of the helium is so small that it may be greater than the weight of the helium balloon, and therefore it can go upwards. Okay, so that's what up thrust is if you're labeling it on an object. But usually in air, usually we're talking about up thrust though in a fluid like water. Drag, air resistance, water resistance. So if you think about it, if you get thrown a ball at you, you feel the force of the ball hitting you. Air resistance, drag, water, it's the same exact thing. If you put your hand out in the car on the motorway, and you experience air particles hitting your hand, okay, and that's what air resistance is. It's just the same thing as if a ball is hitting your hand, but lots and lots of smaller versions of that, and that's what's causing air resistance. So what changes that? Well, if you know when you're a child, you put your hand out in the car window, that the faster the air particles or you are moving, that you would experience a bigger force if you were going faster. Or what else is it going to depend upon? It's going to depend upon the surface area. So obviously a larger object is going to collide with more air particles that are going past it, and that's going to make it experience a larger force. So the faster an object is, and the larger the surface area is of the object, technically as well, it would depend upon like the air pressure. Okay, so there's lower air pressure if you go in higher in altitude, isn't it? So there'd be less air particles. So that may affect it as well, the air pressure. So that's air resistance. Water resistance is the same exact thing, but now not to be confused with upthrust. This is when you're moving through water. So the object, when you're moving through water, is going to feel a backwards force acting horizontally due to the water resistance. So we sometimes just call these drag. You've then got friction, which is when two objects rub against each other, and that causes friction. And then you've got lift, which is on the wings of a plane. It's my plane drawing. So as the plane, I won't go into explain how it works, but as the wings of a plane undercut air, it causes this upward force, which is lift. So it's not upthrust. That's a common mistake that people label on planes, that it's upthrust. It's actually lift. You have tension then, which is just if you were to pull on something, if you're getting pulled on a rope, or then there's just general push and pull forces. Like anything, if you push on something, if you kick a ball, you've pushed the ball, that would be push. Anytime you pull on anything, you would kind of label as just pull forces. So these are basic examples of the main forces that you use at GCSE. So let's now go into the first law of motion, or otherwise known as Newton's first law. Okay, so you may need to know it as Newton's first law. It may just be called Newton's first law of motion. Before I actually give you what the definition of the law of motion is, let's go over some key terms first. So let's think about this first situation here, that we've got two forces acting on an object, and we can see here that these are equal. We've got 250 newtons. Newtons is the unit of force. 250 newtons, and they're acting in opposite directions. So these forces are equal and opposite, and therefore they're going to cancel each other out. They're the exact same amount. Okay, so we would say that this object is balanced. The forces are balanced. Well, what's this object going to do? I bet you can tell me straight away. It's going to stay at rest. Okay, it's going to stay at rest. These forces are cancelling each other out. They're equal and opposite, and therefore this object would stay at rest if it was at rest to begin with. What's the other situation? Well, these forces are acting against each other, but we can now see they are no longer balanced. We've got one force is bigger than the other. So we would call this unbalanced. Okay, and as they are now unbalanced, there is now a resultant force, which is like the net force or the leftover force. So the resultant force is a really key term. So what is the resultant force? Well, all you would do is add up the forces that are acting together and then take away the forces that are acting against them. So here we've got 450 newtons minus 300 newtons. So here the resultant force would be 150 newtons to the left. So how could this change? Well, if someone came to help someone else here and they started pushing again with another 100 newtons here, well, that would be 100 plus 300, so it's 400. So now the resultant force would only be 50 newtons to the left. So when forces are working together, you add them together and then take them away from what they're acting against. So that is the resultant force. Now, what would this object do? Well, it's feeling a resultant force of 50 newtons or 150 newtons to the left. So it was at rest, it's now going to move to the left. So this object is going to accelerate to the left. So it's going to move from rest. So resultant forces cause objects that were at rest to move, to accelerate. Whereas if they're balanced, it will stay at rest. Okay, but it's not this simple. What's the situations that confuse people? So if we stay under balanced forces now, but we can talk about a car. Let's use the example of a car moving on the motorway. And let's say that the car is moving at a constant speed of 60 miles per hour. Okay, so, and let's say it's moving 60 miles per hour to the right. So most people often think like, oh, well, if it's moving, it must mean that the forces are unbalanced. It must mean there is resultant force. And that is not accurate. That's not true. That's the biggest mistake in forces at GCSE. It is still, if it is going at a constant speed, it is still balanced. The forces are balanced. So whatever force is going forwards, it must be the same equal force going backwards. Now, whenever we label forces, we shouldn't really label them like I've done up here. We should always label them coming from the center of the object. And I should take a bit of care now, because I'm saying that these forces are the same. I should make sure that my arrows are the same size. So if this was 500 newtons going forward, they may leave a blank space here, and they'll say, well, if this car's going at a constant speed, what's the backwards force, which would be air resistance and friction here? Well, and then you would need to think, well, if it's 500 newtons going forward, it's at a constant speed, I know that means it's balanced, so there's 500 newtons going backwards. Okay, so think about what's happened here. The faster the car got until it reached 60 miles per hour, the air resistance would be increasing, wouldn't it? Because it's hitting the air particles faster, so it's feeling a great harder force, and that's what's giving it this 500 newtons backwards. So if it's going at constant speed, the forces are balanced. If the car was to accelerate though, so say it was to go 60 miles per hour and it's now changing speed to 70 miles per hour, it's now getting faster, and that must mean that the forces are unbalanced. So say there may be something like this 600 newtons now going forward, and there was still only 500 newtons going backwards. So now you would say that the forces are unbalanced. There is a resultant force of 100 newtons to the right. Okay, so there's a resultant force of 100 newtons to the right, which has caused it to accelerate. So unbalanced forces, so this is now causing it to change speed, to accelerate. It's changing speed. Okay, so let's use the other final example that we need to talk about before I give you the full definition. So let's say that something is going at constant speed now. So we've got a car going around, it's making a turn round a roundabout. And that's going to say it's going at a constant speed of 30 miles per hour. Okay, but what's different this time? Well, it's changing direction. Now, if you think about what you know about motion and what you know about acceleration, well, our definition of acceleration is, you may know the equation, is v minus u over t. So final velocity minus initial velocity over time, or the change in velocity over time. So if something's change in velocity, it is accelerating. So, you could be thinking, well, it's staying at a constant speed of 30 miles per hour. But if we think about what velocity is, remember velocity is a vector. It's the vector version of speed. So that means it's got a magnitude and a direction. And therefore, if it's changing direction, it is changing velocity. It does not matter that the magnitude is the same. It is changing direction. And therefore, it has changed velocity, and therefore it is accelerating. So an object that turns a corner or changes direction in any way, if you were drawing the vectors on here, it was going in this direction, the velocity was. Now it's going in this direction, now it's going here. So it's changing velocity, and therefore it is accelerating. Now, what does that mean? Well, we know if an object is accelerating, that their forces are unbalanced. So there must be a resultant force acting on this. Okay. Now, in some examples, you need to know that if something's going in circular motion, this would be called, which direction is the unbalanced force acting in? This resultant force is always towards the center of the circle. So no matter where the car is, it's always going towards the center of the circle, and that is called the centripetal force. So that's something that catches people out, that just because they've said that it's a constant speed doesn't necessarily mean the forces are balanced at all. It depends upon the direction it's traveling. So in summary then, what can we say Newton's first law is? Or the first law of motion that we need to know about. So Newton's first law, the first law of motion, is that an object will remain at rest or in constant speed and direction unless acted upon by an unbalanced force or a resultant force. So an object will remain at rest or in constant speed, and don't forget that direction, unless it's acted upon by an unbalanced force. Now, what's a simple way of remembering this? Simple way of remembering this is literally that an object will only accelerate with resultant forces only. That's an easy way to remember it. As long as you know that acceleration is change in velocity, which means change in speed or direction, you know resultant force means unbalanced, and therefore you know that, well, if it's stationary, it's not accelerating, therefore the forces are balanced. If it's just moved, it's accelerated, it's unbalanced. If it's a constant speed and direction, it's balanced. So that's a quick way of remembering Newton's first law. Let's do a quick example of something going on using this Newton's first law. Let's look at labeling a force and describing the motion. So let's use an example of a boat, or I'm gonna have to try and draw. Let's draw a jet ski here. So I've got a jet ski. That's my drawing of a jet ski here. And let's say that the question said that the jet ski was getting faster. Okay, and it wants us to label the forces and describe what's happening. Well, if we were to label the forces, we would know that we've got to label our weight going downwards, and we're doing it from the center of the object. Upwards, you should remember now that we can call that up thrust because it's in the water. And we should be drawing those forces the same size because they're balanced. It's not accelerating into the water or going out to the water. Now it's getting faster, so this time I need to make sure I've got a bigger force going forward, and now that would be thrust. Because a jet ski or a boat is pushing water backwards. And then backwards here, I can call this drag or water resistance. I'll call it drag. Okay, and I've made sure that my backwards force is smaller than the forward force because it's accelerating, it's going faster. Now if it's going faster, we know it's accelerating, so how would I describe the forces? This object is accelerating, therefore it is unbalanced, and you may even say due to Newton's first law, and therefore there is a resultant force acting on it forwards, or whichever direction it's accelerating in. The resultant force is always the direction that it's accelerating in. So if this thing was braking or slowing down, the resultant force must be backwards, okay, because it would be deaccelerating. The acceleration would be backwards. Okay, let's use the example of something changing direction. So anytime something changes direction, so they may say something like, they'll try and catch you out with, say something like a I don't know, kid on a skateboard, and they'll make sure they talk about how it's going at a constant speed. Okay, it's going at a constant speed to make you think that the forces are balanced. But anytime it says that it's changed direction, so if the skateboard has turned to the right here in this example, well, we would say that is still unbalanced, and we'd say it's because it's changed direction, and we said that means it is accelerating. Okay, so 2 examples there of something accelerating. But don't forget that first thing we said, that just because something's moving, it can still be balanced. Think of the car going at a constant speed. If it's going in the same direction, it is balanced. So that is Newton's first law, which once you understand Newton's first law and you understand it well, it actually turns into quite easy questions, and students often do well on these types of questions. We'll now move on to Newton's second law in the next video.